Optimize. A Journey Through Database Query Optimization. This course is filmed on location at Carnegie Mellon University in front of a live studio audience.
All right. So today we're going to, as I said, begin the journey of discussing. We know how to now build either top-down or bottoms-up, query optimizer. We know what the basic algorithms look like, how to do transformations. But now the big thing we need to know about is, okay, how we actually do those cost estimations to guide the search. So that's what the next couple of lectures will focus on. So before we get to that, a reminder: Project 1 is we do this Friday, excuse me, the 28th. Post on Piazza as people have done. If you have any questions, some of those submissions have been pretty impressive. What people have done, like copying out the calcite code that doesn't do what you wanted to do, and then modifying it and putting it back in. Anything's on the table. For Project 2, I know last week I was going to follow up people about sending them the topics. I'm behind on that. We would try to get that today. But I'll be around during spring break if you want to discuss the plans for your project or what your proposal presentation should look like on the Monday coming back after spring break next week. So in 2 weeks. So any questions about Project 1? Any questions about Project 2?
So we're going to get assigned today.
Yes.
And then we have this week to make a presentation and we'll present on the following Monday.
Next week, spring break.
Yeah. So we could also work over spring break. I'm saying
That was assumed.
Okay. Okay.
It's grad school, or you're still undergrad. Yeah, well, legally I can't. University policy says you're not supposed to do stuff with spring break, but again, the proposal is supposed to be a 5-minute presentation. It just you want to write up what you're actually going to do. It's better to sort of plan things ahead of time so you know what you're getting into and not just saying we're gonna fork Orca and make all these big changes and it's going to be a nightmare. So think it through first. Any other questions about Project 1, Project 2? All right, for the database talks, we actually slight change in the schedule. So today we still have the P&O people coming to talk about their query optimizer, and what the focus of their talk is going to be about how they actually support 2 different query languages. I think PromQL is the query language for Prometheus, and then I think also they're supporting SQL, but to do time series analysis and how they can convert them into the same sort of relational algebra and have a single query optimizer handle that. Then we have spring break, and I had something scheduled for that. That got bumped. And then we come back from spring break on the Monday. We'll have somebody from Google Research give a talk about this paper they wrote in the last year about adding basically things that look like pipe semantics, or think of it was like a data frame API to SQL, and they have it in their Google SQL proposal. It's obviously meant to be more general, but as far as I know, nobody's adopting this technique. Timescale has something that looks a little bit similar to this, but it's not exactly the same. So they'll talk about, again, this would be an extension to SQL. Then the Mellon guy is going to give a talk the following week. That actually was scheduled for next week. That got bumped to after 2 weeks after spring break. And this is where he had a startup called Looker ML, got bought by Google. They had this new query language that transpiled into SQL called Mellon. He's now at Facebook, Meta, and he's still working on that project. So he'll talk about that. Again, this is an example of one. It's a veneer on top of SQL that then gets transpiled down into SQL. Okay. All right, so last class, we went through what I consider one of the important papers in the last decade for query optimization. Right, there's a lot of papers on this ML stuff we'll cover later in the semester, but this is just straight up algorithm to do unnesting of arbitrary correlated subqueries, which has been something that people have been trying to do for 40, 50 years since the early 1980s. And with mixed success. And so this paper is the paper you guys read, and actually the precursor to it are what I consider to be the definitive guides on how to handle this in a query optimizer to get to convert all the correlated subqueries into inner joins or with additional operators to get really great performance. And so again, if you're building a query optimizer today, which we are, that paper is the go-to guide on how to do this. And it's compatible with a top-down and a bottoms-up optimizer. But again, very few systems actually do this. All right, so as I said, where we're at now in this point in the semester is now we need to have a search algorithm, a search engine that can take a SQL query and start enumerating different possibilities for the plans and in somewhat of an efficient manner and within the constraints that the SQL query is specifying, either through the schema or the query itself. And then now we need to be able to determine, is one plan going to be better than another plan? And this can be done through the cost model. So it's an estimation of what will be the physical cost of actually executing that query for a given database state. The database state will be defined based on the hardware, on the contents of the database, like what's actually inside the tables, the distribution of values, and so forth. Some ways it could also be tied to the configuration, but we could ignore that. But at the end of the day, again, it's a way where to say this plan we think is better than this other plan, or even this operator or subplan is better than another operator or subplan. And that way we can choose that one, the better one, rather than the one we think is worse. And so this is an internal cost. It's not something that's tied to the outside world. There have been attempts to take the estimations that Optimizer makes inside the query cost model and then be able to map that to like real wall clock time. Say, hey, this query is actually going to take you an hour or 20 minutes or something like that. That has been shown to be a very difficult problem. Then there's been sort of a simplification of that to say, okay, well, I can't predict how long a query is going to take, but if I know if it's been running for so many minutes or seconds, don't know at least how far along I am in to finishing, like trying to percentage completion. That has mixed results too. That's very difficult. But again, we can ignore that. We care about just saying, is this plan better than another plan, right? And this sort of goes without saying too that the cost models for various different database systems are going to be completely incompatible with each other. I mean, you can't take a query plan, cost estimate from Postgres and try to compare that with any kind of query cost estimate from MySQL or Postgres and so forth. Some logical things like the estimated cardinality of an operator, that is obviously compatible. But whatever number Postgres spits out, that's a Postgres number. You can't use that for other systems, right? And again, as we said in the beginning, the reason why we're going to have to do these estimations using a cost model is that it's simply going to be too expensive for us to just run all the query plans and figure out which one's actually going to be the best, or even just run individual operators and figure out which ones are going to be the best. Again, we'll see the way Mongo does this later on, but in general, most systems can't actually run queries to get estimates. So there's going to be two components for our cost model. The first are the physical costs, and then the second will be the logical costs. So the physical costs are going to be the end of the day, what will be in the cost estimate for a query plan, and it's going to be how much hardware is the query plan going to consume when it actually executes that particular plan. And so it can be a combination of CPU time, any kind of I/O, either disk or the network, how much memory we'll be consuming to build whatever data structures we need or stage intermediate results as we run the query plan. In some cases, nobody actually does this, but there's been papers that actually predict, well, what percentage of the data is this query going to access will be inside the buffer pool. So I know I'm actually not even going to have to go back to the disk to go fetch things. And obviously that one's really challenging to do because the time in which you're optimizing a query and generating the plan may be completely different than when you're actually running the query. So any estimates you would make on what's in the buffer pool, a half an hour ago are completely useless. Even 10 seconds ago is potentially useless, right? So these estimates for the physical costs, these obviously are going to be tied to the physical implementations of the operator. Like if I know I'm doing a hash join, I'm going to build a hash table. Okay, so in that case, I can estimate how much memory I'm going to have to use to build that hash table. Can also estimate what the occupancy rate will be of the hash table. So therefore, is it a giant hash table where therefore I'm always doing O1 lookups, or is most of them going to be, ON, right? And we'll talk about this a little bit at the end in the class today, but obviously these things are, we're trying to tie this to wall clock time. So we're trying to say like, to do one disk IO, that's going to be 50 milliseconds or 500 milliseconds, depending if it's on the cloud or not, right? And so coming up with the constant weights for these different hardware resources is a really tricky problem. And in some systems, we'll see later in today's class, they'll actually run some kind of benchmarks to figure out what are the values for these things. Whereas Postgres relies on you to tell it what these how much does the CPU cost versus disk I/O cost. But the high-end systems will try to figure this out for you. Then there's this notion of a logical cost. And the idea here is that, just like before when we had the logical operators and the physical operators, the logical operator represents the high-level task that we're trying to perform, like a join. And it's not specifying what the implementation or the algorithm we're going to use to compute that join. So therefore, the logical costs are independent of the physical algorithm, the physical operator. And so the most common thing is going to be, the most important one is going to be, and the whole next class will be on this exact problem of how to estimate how much data is going to be coming into my operator and how much data is going to be coming out of my operator, right? And this will be cardinality estimation. And this is what we'll discuss on Wednesday this week. All right, again, think about this. If I'm doing a sort merge join versus a hash join, the join predicate is still going to be the same, right, for either of those physical operators. And therefore, the number of tuples that are going to be filtered or not filtered coming out of that operator will be the same regardless. And again, that's why it's a logical cost, and we can compute this without having to know what the physical implementation is going to be. In some cases, we also can compute things like how wide are the tuples going to be, like how many columns per tuple. And you can start doing this, you could use this to decide whether you want to like projection push down or you're doing late or early materialization, right? If tuples are really wide, maybe you don't want to pass all of them up through the operators, right? Because you're copying useless data, and therefore we want to push down a projection or something, right? But in general, the one we care about mostly is this one, right? This one you can derive. If they're fixed length things like integers, they're easy to do. If they're from, if you're coming from like text columns, then you got to look at like what's the distribution of the length of the strings, and then you have to get that from statistics. We care about this one, and obviously, if we have this, then that's essentially how we're computing this, right? So again, if I'm doing a scan and I'm trying to estimate, okay, how many tuples am I going to have to scan and spit out? Well, I can just go look in the catalog and say, well, how many pages is this table occupying? Therefore, I know that's the number of things I'm going to have to scan, the number of pages I'm going to have to scan, and then I can just multiply that by whatever my weight factor is for doing disk I/O. Now, how to handle sequential versus random, that becomes more tricky, right? Obviously. But again, the idea is like you figure this out, and then you have some constant weights that you, for your formulas up here that tell you, okay, how to convert this into this. Logical costs we've already seen before. We saw this when we were talking about the branch bound search. We do predicted cost bounding. Like we were using logical costs and say we expect to get X number of tuples out from this operator below, and therefore I could decide to cut off exploration of that branch going down if I didn't think it was actually going to be fruitful. Logical costs are basically also the same thing for promises as well, right? It's helping you decide, all right, I think that this operator is going to generate a lot more tuples, and therefore I should explore what the best way to optimize that is first versus something like it's going to read 1 tuple or 10 tuples, right? You want to spend more time exploring the different physical operator choices you have for the operators you expect to have the highest logical cost. And therefore, you would get the most benefit if you figure out the best operator implementation for it, right? But I'll just point out that, like, well, people may think, oh, if it's the logical cost, that's going to be way cheaper to calculate than the physical cost, right? The physical cost I was saying is a combination of all these things, and I'm saying the logical cost is like, oh, the cardinality estimation. This cardinality estimation, right, that you're going to use for the logical cost, that's actually the most expensive thing to do, right? Because that's, again, looking up in the statistics catalog, which we'll talk about in a second, and then applying some formula on whatever data structures you've maintained for the, for the data summarizations for the tables, right? That's the expensive part. Chugging a bunch of constant factors in based on the number of tuples I expect coming out, that's relatively cheap. That's cheap. That's easy math. It's deriving the logical cost is actually the most expensive thing.
But it's also more inaccurate, right?
The logical cost?
No, converting logical to physical.
Statement is the conversion of logical to physical up here, did that introduce additional inaccuracies? Yes. Well, right. So this is my parting thoughts for today's class. This is all a house of cards. We're building approximations on top of approximations. We're making other assumptions about the data. It's all a way to simplify the problem because you can't actually go run things for real. So to your point, yes, these weighting factors, if it's Postgres and I'm punching in some numbers myself, yeah, that's gonna be problematic. Even if it's like Oracle DB2 trying to derive these as well, like that's hardware's never deterministic and always has the same performance for everything at the same time, right? Because there's so many different caches and things like that, different levels of abstraction. So yes, so this is an approximation. This is an approximation. So we're approximating this by taking this approximation. Yeah, so it's all a mess. But again, there's no way, there's no magic wand to get this. Okay, all right. So today I want to briefly talk a quick background of what does it mean to maintain statistics inside of a database system that we're going to then use for the optimizer to make cardinality estimations and other cost estimations, right? It's really about understanding what data structures are being maintained, how we're going to generate them, to then again feed into later parts or next lecture. So we'll talk about the three main categories: histograms, sketches, and sampling, and then we'll briefly talk about what real-world implementations actually look like, at least for the open source ones that we can see, right? Again, the idea is that we talk about these data structures today, and then next class we talk about how to derive the cardinality estimations from the data structures. All right, so when someone says they have the statistics in their database system, right, it basically means the data structures that the database system is going to maintain that are going to summarize what the real database looks like, right? And there's a bunch of different choices, as I just said, like of different choices of what data structures you want to use. But even within the data structure choice, there's a bunch of decisions we can make about how much space to allocate for that data structure, how aggressive we want to be in updating it, the data structures when our data changes, or when new data arrives, right? And so the things we got to consider is like, how much accuracy do we care about? Can we even quantify what that, the confidence intervals might be for the data structure we're using? How efficient it is to maintain it and update it and keep track of things? How much memory we're going to have to maintain for this? Again, even though we are going to store this in our as our statistics, just like a regular table in our catalog, that get written out the disk like any other data. In order to use this information, we got to fetch it back into our buffer pool and then extract the information we need to do our cost estimations. So if our database is 1 gigabyte, but our statistics are 10 gigabytes, that's not a good trade-off, right? Because that's now taking its memory pressure in the system that could have been used for running queries, but instead you're maintaining the statistics. How good is the coverage or the applicability of the data structure is going to matter a lot as well, right? Like some data structures we'll see, like Countment or for the hyperlog log, it can only tell you the number of distinct elements you have, but it can't do any additional filtering beyond that. Like it can't tell you things like the number of distinct elements I have with that are with values within this exact range, or for values that end with the letter ABC, right? It can only give you sort of coarse grained approximations. And so we'll see the fallback data structure everyone's going to rely on is going to be the histograms, because those you can handle pretty much any query predicate you may deal with. But the other ones are going to be for certain cases will be much better. And then of course, as I said, how are we actually going to build these things? When do we actually build them? And how do we maintain them? So as I said, the database system basically stores statistics. At least most systems will store statistics just in its internal catalog, right, where it keeps track of the metadata about here's the tables I have, here's the columns I have, here's the types and so forth, right? The PG catalog if you're familiar with Postgres, or an information schema in some systems, right? And these are just tables that are stored like any other tables. There is a little magic to them, because you're basically, they have to the catalog has to be bootstrapped. Like you can't have, if you need to know if you need a catalog to put anything in the catalog, you obviously need a catalog. So look at this weird circular dependency. So a lot of times the statistics in the catalog are sort of bootstrapped with hard-coded commands, and then everything else just inserts them like regular tuples, right? So again, we're going to store this in our database. We can look at that in a second, what it looks like in Postgres and other systems. And then there will be some mechanism that the system is going to have to decide when it actually either wants to create them or update them. In the case of something like Postgres, they had this thing, the auto vacuum, is basically the garbage collector where it cleans up the old multi-version tuples. So they just piggyback off of that. So when the vacuum runs, they'll actually then recompute statistics on a block-by-block basis, and to keep track of which ones have been updated since the last time they passed, and which things get updated further, right? Some systems, like Oracle, have a fixed schedule. I mean, you can adjust when it occurs, but basically, in Oracle, I think by default, every night at 10 p.m., this or UTC, whatever your time zone you're in, at 10 p.m. by default, it fires up and just starts scanning all the data and computes statistics, right? Updates all the internal catalog information. Oracle does other cool things like figure out what queries are bad, maybe run them through the optimizer again, and then try to come up with better query plans in the background so that when you run them again, it has a better plan for you, right? Obviously, most systems will have a modification threshold to say, if I've updated 20% of the data in my table, I'm going to assume my statistics are out of date, and therefore that triggers a rebuild of the statistics. And then, of course, the backup choice would be just do manual invocation, where some administrator, some user can then fire off a command, and Postgres is analyzed. I forget what the SQL standard says, but in like SQL Server, I think Oracle, you call update statistics, and that forces it to then scan all the information to repopulate its statistics in the catalog. All right, so let's look at some quick examples. And again, the catalogs are just tuples, right? Like they're just regular data. They obviously have this special meaning because it's being used for statistical information. But you can just go look at it and see, what's actually in them. So let's use Postgres. So Postgres has this table. It's a view. It has PG stats and there's PG statistics. PG stats is just a view on top of PG statistics. But I can go and say, select star from PG stats where table name equals enrolled, right? And actually I got nothing, which surprised me when the first time I ran this, because I was like, wait a minute, this table exists. There's something in it, right? I can do select star from enrolled, right? And there's data in it, but there's nothing in my statistics. So I can force it, if I run analyze, and then pass in the name enrolled, that takes 8 milliseconds because there's only 6 rows in it. And then now when I go back into PG stats, that's hard to read. Let me fix that. Right now when I go back in PG stats and I get all the records there for this table, now you start to see what the statistics is going to be maintaining for every column in the table, right? So you see at the top it says schema name public, and then the table name is enrolled, and then the attribute name is the column name, SID, student ID, and then here's course ID. And then so Postgres, we'll talk about histograms in a second. Postgres is going to maintain an equidepth histogram where it basically groups up the ranges of values that are going to have basically the same total count of number of elements. So it'll maintain that data structure for a histogram. And you can see, where is it? There's common values, average width. The histogram bounds is null. Let me go down here for this one. We have to look at a better example. Yeah, the histograms are null. Maybe because it's so small, it doesn't do anything. But here you have the most common values and most common frequencies. So this will be like the n bias histogram we'll see in a second, right? The same 15721 is most common, and then 1545 is the next most common one, right? And again, if I go look at the schema of PG stats, there's nothing fancy about it, right? The histograms are just arrays. The most common values are just arrays. Any array means it's an unknown type at the time you're putting things in, all right? It's just tuples with arrays, right? And the optimizer knows how to interpret those tuples and those arrays to say, oh, I know it's a histogram. It knows how to read the values, read the other attributes, and get the information that it needs. Let's look at more. So this is the database from DBDIO, the database of databases. But I just want to show a more busy table, right? So now this is what a real table would look like. Now you have histogram bounds, doesn't have the most frequent values. Just scrolling down, this thing is huge, right? No. Right, here's what are these? These are timestamps. So it's keeping track of the histogram bounds. The most frequent values is useless because they're just timestamps. They would never be the same. So there's some logic here where Postgres is trying to figure out, oh, I don't see a lot of different values, therefore I don't need to maintain maybe the full histogram, or I'm seeing nothing but completely different values, so therefore I don't keep track of what are the most common values, like the heavy hitters. But I will point out, Postgres is maintaining stats for everything, right? For scrolling down here, I have certain things like, here's a bunch of people's names, and they're always going to be unique. Or here's the here's a bunch of logos for the various database systems that are keeping track of the URLs in the database. Like, I'm never going to run a query select star from table where I'm looking for this information, like someone the logo. Maybe I am, but assuming I'm not, right? But since Postgres doesn't know what queries you're going to execute, it still maintains everything. In some systems, they will actually watch what queries you're running, and they figure out, oh, I see you care about this table and this column, so therefore, let me go get the statistics that you're going to need later on. All right, so quickly, let's bump to the other ones. We can do MySQL. I wasn't able to figure out how to get good information out of MySQL, but they had this thing called information schema.statistics, and it's basically you can see what metadata they're maintaining about every different columns in this table. So there's a student ID and the course ID, and then you can see things like it's keeping track of the cardinality, whether it's nullable or not, right? The histogram's in there somewhere. I haven't been able to find it. We can go to SQL Server. So SQL Server has this command, thanks to ChatGPT, called dbcc show statistics, and you get nice information like here's where it keeps track of the statistics. Here's the last time it was updated. Here's the average length of the data being stored in that column, and then within the column here's the values, the number of values that match up. This is basically the histogram right here, right? Again, it might be sorting some additional more sophisticated things underneath the covers, but as far as I can tell, well, I don't know whether they're storing this as regular tuples like Postgres does, and whether this is just a view on top of whatever the internal data structures are. Because obviously I ran some command. Maybe this got translated to a SQL query. I don't know. But again, it's basically maintaining similar things to Postgres. The last one I'm going to show is this Oracle. I don't know how to get the stats out of that, but I just want to show you this scheduling thing they have. Right, so they have DBA scheduler window groups. So this is all the maintenance tasks that'll execute on a nightly cron job automatically for you. So here it's going to run whatever the 24th is. That today? Yeah. So today is going to run at 10 p.m. UTC, which is what now 2 p.m. But the things that's going to run for you is the tuning advisor, right? They tell you where you have crappy queries, and then in here somewhere, you should run the auto optimizer stats collection. So it'll run basically analyze automatically for you. It does this every day. Because that's oftentimes what people have. We have crappy queries. They're like, why is my query so slow? Oh, it's because you have bad statistics, right? So what I'm trying to say here is there's nothing magical about these statistics. All these data structures we're talking about today, we can just chuck in the in tuples in our catalog. There's nothing special about them. All right. As I said, most data systems will create single column statistics for each column in a table when you first set up the table and start putting data into it. And other systems will wait to see what queries you're actually going to run first. But in general, it'll maintain what are called single column statistics. So basically, for one column, here's the information I need to know about it. The challenge is going to be, and we'll see more of this next class, is that sometimes you want to know whether columns are correlated, right? Zip code and city, and for addresses, that's definitely correlated, right? Zip code can, if for a given city, you're going to be in one zip code. So in some cases, the data system, I don't think anybody can try. I don't think any system tries to figure this out for you. You definitely have to be. I know you can tell it, but you basically what are called column group statistics or correlated statistics, where you basically can build multi-column statistics. I think they have to be in the same table so that when a query shows up that maybe references both columns in the where clause, instead of looking at the single column statistics for each of those columns one by one and making assumptions about the relationship, I go look at that multi-column statistic I've generated, and I can get better estimates. So let's do a quick example of that in Postgres. Postgres has this. So let me pop out of this. So I'll create a simple table, XXX. And I'm going to put in, put a million tuples in. So what it's going to be is I'm going to put a million tuples in where the first tuple is going to be whatever this value 1 to a million, and then actually both of them are going to be values 1 to a million, but I'm going to mod it by 100, right? So in this case here, the values for the first column and the second column are going to be exactly the same, and then within the distribution from 1 to a million, it's going to be repeated for every 100 values, right? So if I now go to my, I can go see how much data I actually have now, right? There's nothing in here. That sucks, right? Because I don't think it actually ran anything yet, right? So I run analyze on it. Now I go back, right? Now I have some statistics about what's in it. So in this case here, even though I just inserted a million tuples, Postgres didn't update its catalog and say, here's how much data I actually have. It's only until I go run analyze, then it actually does it, right? If I do that query I did before with PG statistics, right now you can see that now it populated the histograms with a bunch of information. So that's good. Okay. So now though, if I run a query that just looks at one attribute, say it is a equals 1. So here I'm running explain, but then you pass a flag and say analyze, so that is actually going to run the query, and then the timing off just gets rid of the timing information for each operator, right? And so now here you see that the estimate is that it's going to generate 4,695 tuples, but it actually generated 333, right? And then you have the estimate for the number of rows removed by the filter. All right, so that's fine because it's a single column. It could use those single column statistics. But now if I do a conjunction query where A equals 1 and B equals 1, which are going to be the same, because again, remember, when I inserted them, they're just the same values. When I run this, now you see that the number of tuples I'm going to expect to filter away is way higher than what I think it's going to be, because it's assuming that these two clauses are independent, A equals 1 and B equals 1. So it says, okay, well, the distribution of this, the probability that something can be selected by this and this are independent, therefore I can multiply them together and get what I think is going to be the true selectivity of the predicate, right? But now if I go back and I can actually create statistics in Postgres. So this is saying create statistics called correlated stats, right, the name, on the table dependencies. And I'm telling it I want it to be on columns A and column B in XXX, right? So that builds that, but I don't think it actually generates anything, so I got to run analyze. So we're good there. So then now when I do explain again on that same query, now you see that the estimates are more accurate because now it knows that these things are correlated using those correlated statistics, and then I get the true selectivity and not the sort of overzealous one, where I'm underestimating the number of tuples I'm going to omit, and this one is actually more accurate, right? So again, you're able to say that these two columns are going to be used together often in queries. Therefore, when I generate these histograms and all these things I'm going to talk about next, base it on both of those columns, not just one by itself. Okay. All right, so how can we summarize things? And again, this is what the chapter in the book you guys read today. There's obviously going to be histograms, the classical approach in database systems. Sketches would be these newer probabilistic data structures that can give approximations for different types of queries. Sampling will be a way to basically get a subset of the base tables I'm trying to scan in my query. Either get that subset by looking at the data itself or maintaining a little reservoir on the side with the information. And then now I compute my estimations based on that sample. And then the last one would be machine learning models, with sort of magic way to estimate the selectivity in predicates by extracting some kind of summarization in some kind of neural net or model later on. So the most common one, obviously, going to be histograms. Sketches are becoming more common these days. Most of the major systems are going to use some combination of these. Sampling is still very rare. SQL Server does it. I don't think anybody else does. At least I'm not aware of anybody. And then machine learning models, we'll read some research papers on this. As far as I know, its use is very, very, very limited. and certainly not to replace, histograms and the other structures yet. Not to say that it can't, I'm just saying that we're not there yet. All right, so histograms, and this should be somewhat review from the intro class, but again, it's a way to just approximate the distribution of the values that we have in a column or multiple columns, right, that we can then use for cardinality estimates. So say this is this is the distribution of values we have, and then for every single time I see the value again, I just increase the counter by 1. And obviously the downside is going to be if I maintain this exact histogram like this, for columns like, an incrementing, a serial column where just, every primary key or every value is going to be unique and is added 1 as you insert new things, then maintaining this can be super wasteful because now for every single value I have in, a billion tuple table, I have a data structure that keeps track of like, oh, I've seen it once, right? So for small data sets, an exact count, this histogram might be okay. But obviously for the more general case of larger data sets, this is not going to work. And that's why you see the way to, in these additional data structures, the additional histograms, it's basically compressing down the exact values that we're storing in exchange for a loss of accuracy. So the first approach would be to do echoed width histograms. And the idea here is that instead of storing exact counts for every single individual value that we have, we're just going to group them together in equal size buckets, right? Just take the number of unique keys divided by some whole number, and then now for each of these buckets, I'm just going to add together the individual counts of all the keys in that bucket, and then represent that now in my histogram. So again, now I'm compressing the amount of data I have to store in my histogram for each, because since it's now only 1 count per bucket. But obviously now I have to then approximate, or to make some guesstimate about what the distribution of value is going to be within that bucket. And the simplest thing to do is just divide the number of keys I have in a bucket divide the count by the number of keys that I have, and assume that each key occurs the same, which obviously we know in skew workloads, real workloads, is not going to be the case. So a better approach is to do what's called an equidepth histograms, and this is the most common one. Postgres uses this, SQL Server uses this, where you basically, instead of having fixed length or fixed number of elements per bucket, you're going to vary the number of keys you have in the bucket, so that, and all you really care about is that the count or the population of the bucket is going to be the same across all the buckets. So in this case here, the first bucket I'm going to go through 1 through 5, the count will be 12, but in the second bucket it's 6, 7, 8, so only 3 elements versus 5 elements here, but the counts are the same, right? So I'm still going to do that trick where I just take whatever the count is within 1 bucket and divide by the number of keys that I have in the bucket. At least now I'm getting a bit more accurate of those estimations than I would have in the equidepth one, right? And the research shows that the equidepth histograms have better error rates than the equidepth histograms, right? Sorry, question or no? Yes.
Doesn't this cause a problem? So if you run analyze, obviously when you do the analysis, you get the right answer. But if I'm inserting tuples into a database after we have this pre-computed, is it recomputing it for every tuple you add, or is it obviously if you add, you can change the skew and get off?
So his question is, how's this actually being maintained? If I'm inserting new tuples, if I insert new tuples and say I'm inserting a bunch of 3s, and all of a sudden this count's going to spike up, and now the height of this thing doesn't match anyone else, what do? So you let it be wrongish for a while, and then at some point you say, oh, well, the data has changed so much, I know I need to recompute this. Another way to handle this would also be, the Postgres doesn't do this, you could partition this data structure on ranges of blocks or pages. So you would say, okay, the first 100 pages, here's the histogram for that. For the next 100 pages, here's the histogram for that. And if most of your action, the new updates are happening in the latter half of the pages, it doesn't change affect the old one. Now, how do you then combine the histograms, right? And then merging them back together, that'll produce incorrect estimates. But at least in that case here, you're sort of isolating the damage, if you will, the inaccuracy to some portion of the histogram space. Okay, again, this is the most common one. And then the it's usually combined with what are called heavy hitter data structures or n-bias histograms, where you basically identify what are the keys that occur the most often, and therefore I'm more likely to query against them or know that these frequently occurring keys are going to have the most effect on the distribution or the cardinality of my operators when I'm executing things. So instead of trying to lump them in with all the other values, you say these guys are special because they occur the most. So I'm actually going to maintain exact counts for those keys that occur the most. And then everyone else is sort of gets lumped into this R bucket here. We just take whatever the average count was for all of them inside that. Again, we saw that in Postgres. They didn't actually maintain this R piece here, but they had a separate list of the heavy hitters, right? Just without this. So they had this, but without this step over here. And again, the idea is you assume that these keys are occurring the most, therefore are going to be used the most in queries. And therefore, I'm going to have accurate statistics now because I'll know the exact count of these things. Notice also, it doesn't tell you where these things actually are going to appear in your table. Right? The relational model is unordered, right? Assuming we're not doing cluster tables, right? So this is just telling you that this thing is going to exist in your table, in your data set for this given column. It can't actually tell you where it would exist. Because in some cases, if you knew where it was, right, you could be a bit more strategic about deciding where to start scanning things if you're doing a sequential scan. But these data structures don't have any of that. All right. So next category of data structures to show up are sketches. And these are going to be similar to the histograms where there are approximations of what the actual data looks like. But they're going to be probabilistic data structures that are going to exploit some aspect of information theory that allows us to reduce even further how much data we actually have to store in these data structures. But in exchange is going to be we'll get worse. We won't get the full expressiveness and capabilities or applicability of histograms for all possible queries. Like these have to be very narrowly used for exact questions, like how many keys exist in my total table. But it won't be able to, but these end up being more accurate than histograms and much easier to use. So I think probably, Bloom filter is an example of this, although it's not exactly the same. Just it's a filter to tell you whether something exists or not. That's an example of something you could use for this. But obviously, if you're trying to do a lookup like where ID equals something, you could use a Bloom filter for that, but you couldn't use it for like ID less than something, right? Because it has no notion of order in what it's storing. So count-min sketches are basically counting Bloom filters. Hyperlog are super common to do the count number of distinct elements. Some systems like Redis will actually, VoltDB will expose this to you. You can say, create a hyperlog for me. Postgres has an extension to do this. And that's like, so it's not for statistics internally for the query optimizers, for the application. You can get directly to a hyperlog. There's a bunch of open source implementations. Probably the most famous one is Apache Data Sketches. It originally started off in Java, and then since then it's been expanded to now be in, I think, C++ or C. I think they have Python versions of these things. Google's Data Sketch has a optimized version of the hyperlog. This was supposed to be a counter or alternative to this. The last update was like 3 years ago, and as far as I know, I think it's dead, right? But Data Sketches is probably the most common one if you want to use something to get started here, right? And it's pretty baller. If you go to the homepage, they have this quote here: "A truly excellent example of theoretically informed algorithm engineering." Graham Commode. That's the guy that invented count-min sketch. Like that's how you know you're a badass professor. If like you're being quoted on something you actually didn't write at the very top. So that's impressive because again, they have implementations of a count-min sketch inside this. I think he was a professor in the UK. He might be at Facebook now or Meta now. All right, so count-min sketch. You can think of this just as a counting Bloom filter, right? Where we're going to have this multi-dimensional array. We're going to keep track of counters and then we're going to increment every single time some key exists. So think of like as I'm inserting data, or if I'm running analyze, which is just a sequential scan that updates these sketches or these summarizations. As I see every single key within a column, I'm going to go insert it into my data structure, my count-min sketch. So say I'm inserting ODB, I'm going to have a hash function that corresponds to each sort of row within my array. And then for each of these, I'm just going to mod it by the number of bits I want to maintain in my array going along horizontally. So the first case here, I end up with hashing mod 8 equals 6. Then it ends up here. And then so I just go into that cell and just increment whatever the value is by 1. Right? So they're all zeros here, so I'm going to add 1 to it. And I do the same thing for all the other ones. Right? So again, as I'm scanning data, I'm doing this hashing and updating this sketch. Then now inside the query optimizer, right, assuming this thing gets populated with a bunch of other stuff, now for my query optimizer, I want to say, okay, how often does this key occur? And again, we'll see this in this class, but like think of like if I know I'm doing a join on a column, and in the where clause it says like where name equals ODB, I want to know how many tuples I expect to come out of the right side and left side of the join, because it's going to help me determine the ordering of the join. So I'll just basically do the reverse of what I did before. Take the 4 hash functions, hash it, mod it by 8. That's going to point to a bunch of different cells. And then now I just take whatever the minimum value is for whatever cell I'm pointing to. And that's going to give me, again, the approximation of this particular key here. Right? Again, it's not a false positive like you could have in a Bloom filter, because that's like a set membership. Does something exist, true or false? This is like an approximation of how many times you've seen a given key in the sketch here, and it could be wrong, but it at least gives us an upper bound for the maximum number of times we expect to see this. So I know that for this given key, I'm not going to have seen it more than 2 times. I might have seen it less than 2 times, right? Because somebody else might have hashed the same cell, updated the counter from 1 to 2, right, which is a different key. But at least I know I'm not going to see some higher number, right? Again, this is going to be helpful when I want to do cardinality spacing for joins, because now, assuming I have assuming I have the predicate of what the key I'm being passed in, and because the associativity clause, I know I can transfer like that key from one side of the join to the other side of the join. I'll have a good estimate of what the number of tuples each of the scans below my join are going to produce. I'm assuming they're coming directly from the tables, and I have this sketch, right? The challenge is going to be if now I don't have something like this, I don't have like the actual constant string I'm going to do a lookup, and how do I actually then do estimations like for every single key from this table, how many times do I expect to see it in the other table? Like the Countman sketch won't help with that, because you basically have to go scan one of the tables and then probe the Countman sketch.
I think the quality of this also very dependent on the number of buckets you have, right?
For all of these things, yes. The statement is the quality of the estimations, the approximations, is going to be not only like the number of, I mean, both dimensions, like how many bits I'm going this way and how many arrays I have going down. Absolutely, yes. And as I was saying before, like, I could have this massive thing that's like 10 gigabytes for a 1 gigabyte database. That's going to be super accurate, but it's wasteful. So what's the right size of this? I mean, there's some formula online that basically says how to do it. Right. And again, like it's I think like the default for some places, like for Apache data sketches, like it might give you, when you punch in the number of keys that you expect to have, and then it'll give you like a 2% error rate or something. So combination sketches are super common. But again, you can't use it for all possible cardinality estimations you may need in your optimizer. The other one that's super common is also hyperlog. And there's a way to do the estimate what's the cardinality of some set of tuples coming up from in an operator, right? Again, if it's a base table, I could have this. If you're trying to estimate the what's the cardinality of some set of tuples coming after you compute a join or another operator executes, unless you're building this hyperlog as you're actually doing whatever executing that operator, then you're not going to have this kind of estimate. So this works pretty simple, except for the harmonic mean stuff. We can hand wave over that piece. The basic idea is that anytime I want to insert a new tuple into my table, I'm going to hash it once, and then I'm going to look at the bit sequence that comes out of the hash, right? and I'll take the rightmost bits over here. I'll say I'm just taking the 2 bits, and that's going to tell me which these buckets or registers they call them that I'm going to update. And then now for the remaining bits, I'm going to count the number of zeros I have going from left to right until I have my first 1. Right. For this simple here, I've 2 zeros, add 1 to that. Right. So then we'll have 3. So then now I take whatever the value I have in this count here, take the max of whatever is inside it currently, and where my first 1 appears for this key. Take the max of that, then update that, and now you got 3. Right. Again, you just do this for all the keys as you're scanning the table. And then now to do estimates, you're basically going to compute, assuming this thing's got populated, you compute the harmonic mean with a little fudge factor in there to handle bias. And again, that'll give you some theoretically bounded estimate for the number of keys that you have. Right. And the general idea is that by counting the number of zeros in the objects that we're storing, this is going to be, it's a way to estimate what's the probability that some number is going to be occurring. Right. All right. So one thing you can do with sketches that I think is easier to do than with histograms, unless because you may have different bounds with histograms, or so the bucket widths of the histograms, is that you can combine them pretty easily. So doing what I've said before, like I can maintain a Countman sketch for different parts of my table, and then now when I want to say, okay, give me the Countman sketch for the entire table, I can just take the buckets I have and just union them together, right? Take whatever the max count is, or actually add them together, and that'll give me the what's the total sketch for the entire table. So it allows you to decompose the problem of maintaining these things into independent pieces, and then at runtime you can put them back together without any loss of accuracy. All right, so the last technique is to do sampling. And the idea here is that it's super hard to maintain accurate statistics in either sketches or histograms. And so what I can do instead is just look at a random sample of whatever the target data I'm trying to access in my optimizer or in my query plan, and then basically run like a mini query where you're not actually producing any results. You're just trying to see what the selectivity estimate is for your predicates. And then you use that information to feed that back into now your optimizer to decide how, what's the Cardinal estimates for different operators. So the 2 approaches to do this is basically you maintain a copy on the side of whatever data you have. Typically you want to keep it obviously small and in memory. And then now you run all your estimates on this thing. And obviously as the data changes, you periodically need to go through and refresh this. The alternative is that assuming all the data is local, like running on the same box as you could just run queries directly on the table you're trying to access anyway. Assuming it's transactional, you run this as like in a read uncommitted mode, so you're not interfering with anybody else running at the same time. And then this will give you some sample of the real data. And the challenge of this one's going to be if other queries are running at the same time and updating the database while you're trying to do this estimates on the actual table itself, you may seem to see the same logical tuple multiple times because things are churning through and you're just sort of blindly scanning and reading stuff. And values may jump around as tuples are updated. So as far as I know, nobody does this, especially in the modern era with like data lakes where you assume that the database is a bunch of Parquet files sitting out in S3, and it's going to cost you money to go get them. It's going to be super slow. So that nobody does this. I mean, Mongo's, they're not really sampling, they're actually just running the queries. You could argue Mongo's doing this, but they're not actually feeding the cost estimates back to the optimizer. It's just the query itself they're running. And so, like I said, SQL Server I know does this, but it's very limited, and you have to turn it on. I think it's not on by default. All right. So again, the basic idea is that I have some query where I have some predicate like where age is greater than 50, and I have my original data set. Assuming I have 1 billion tuples here, right? So I'm just going to scan through, flip a coin. I can either do this at the block level, or I could do this on an individual tuple level. Assuming I'm doing an individual tuple level here. So now I have this table sample on the side here. It basically has the same schema as the original table. You can remove derived columns, anything fancy, but you have the basic data of the table here. And then now when I want to get the estimate for my predicate, right, where age is greater than 50, I could, instead of looking at the histograms, I just scan from beginning to end on this sample table and then find the records that match the selectivity. And then that's going to give me the estimate that I then say, right, assuming this sample is representative of the entire data set, here's what the cardinality estimate is going to be, or here's what the selectivity estimate is going to be. So this is nice because, again, I can handle any possible predicate, any kind of where clause, because it's going to be the same query engine as I'm running the query in the real system. But maintaining this is non-trivial and expensive. So again, most systems don't do this. But I think in practice, this shows you, I think research shows that this actually produces the best estimates. I think, and the paper you guys read next class, I think covers that. All right, so any questions about sampling, histograms, or sketches? As far as I know, Calcite does histograms and sketches, right? They don't do sampling. Orca does histograms and sketches. Postgres only does histograms, and the newer systems will do a combination of both of them. All right, so we talked a little bit about Postgres already, but
We didn't cover the ML approach.
all right. So question: we didn't cover the ML approach. There's a whole. That's like lecture 18, 17. Yeah, that's later. Yeah. Are you disappointed, or
I would want to learn it.
that's what it's on the schedule, right? Nobody does it though, right? But it's like super early.
But it seems like a really cool idea.
What's that?
It seems like a really cool idea.
It seems like a really cool idea. I mean, that's what those were, right? Like, no. So like to me, it makes sense because think of, like it's still early though. Like the early implementations could only do predicates like where something equals something, and then it got a little better. Now it can do less than and greater than, but it can't do like clauses. It can't do in clauses, right? There's still limitations of what they can do, right? But the way to think about it is everything I've shown here is like smart humans are deriving these data structures and algorithms to extract the cardinality estimates of them, right? And the idea of machine learning is there may be implicit correlations and implicit signals in the data that a human's not going to be able to see, and therefore I can train a machine learning model to identify that and figure that out for me automatically. That's the promise.
Like a very easy approach would be the histograms that you were showing, and then the condensed versions of them, right? The equivalent. That conversion, I feel like an ML model would do significantly better than picking any random metric.
The statement is my example of like the equa depth histogram that I was hand waving how we're going to pick what the buckets are, and in most systems it's going to be some kind of, actually all systems, it's going to be some kind of heuristic that says here's what the balance should be, and that it's a machine learning model could do something better. Sure, but like it's like
So we could use a machine learning model to come with better sketches.
so we're going off track here. We'll come into this later. So we will see papers. IBM has actually done a lot on this area, and the challenge has been is like what happens when the thing goes wrong. And so I forget whether I signed this paper or not, but they have a bunch of fail-safe mechanisms that like if the ML model looks like it's getting shit wrong, then it falls back to like the sketches and histograms. So you still need both. And so yes, is ML going to be the future? Yes. Right now, the current state of the art is like you want both because ML can't do everything, right? And there's a cold start issue. There's a bunch of challenges. But again, we'll spend a whole lecture on this later. All right, Postgres, as we already talked about, right? Its physical cost will be estimated based on the combination of the CPU, the amount of CPU you're going to consume, and the I/O cost. But then the way that they're going to determine how much time or work, a piece of CPU work versus doing some kind of I/O is going to cost is going to be based on these magic constants you have to specify when you configure the system. So by default, it assumes that you're going to be running on a disk system that doesn't have a lot of memory, and that the cost of processing a tuple that already exists in memory is going to be 400x faster than reading from disk. And then they have, you can also separate between what the cost of sequential I/O versus random I/O, like scanning a table versus probing an index, right? So if you go read the Postgres documentation, they had this huge disclaimer here that says, unfortunately, there's no well-defined method for determining ideal values for the cost variables. They are best treated as averages over the entire mix of queries that particular installation will receive, right? That means changing them on the basis of just a few experiments is very risky. So they're basically saying, like, if you run a few queries and see what happens and try to tweak these values, you may end up with bad cost model estimates because there's so many different factors involved in the hardware. And they're just basically stripping it down to like a single value. Hey, random IO costs this much more, this much less than a CPU, right? So this is where machine learning does help. I had a startup that did this. They try to figure this out for you automatically, and it made a huge difference. But again, in case of Postgres, they're relying on you to either run that machine learning algorithm or figure it out on your own how to set these things. And nearly nobody knows how to set them. So in the high-end systems, what I'll call the enterprise systems, what they have is the ability to automatically figure out what these constant weighting factors should be. And they can do this. They'll do this either when the system boots up, and then periodically, every so often they'll run something in the background, similar to what Oracle does, and then they'll figure out these weights for you. So that way, if hardware degrades over time, or like you install the system on one SSD and then you swap out the SSD and put a better one in, or you put more RAM in, then it can update itself and update these constant factors without you having to rerun experiments manually or run some machine learning algorithm to figure out what they should be. So System R actually did this back in the day in the 1970s. Like a lot of things System R did that like modern systems use today, like basically they did everything back in the 70s. They did code generation. They did alternative storage models. Like they did a lot of interesting stuff back then. So they would basically had a bunch of humans write these synthetic queries to go like sequential scan something or do an index probe. And they would then run those experiments in the lab. And then that's how they figured out what the constant factor should be. In the case of DB2, when the system boots up, they run a bunch of experiments automatically, then figure out what all these constant factors could be. And as we said before, machine learning can help figure this out as well. So DB2, right? They have a bunch of micro-benchmarks that when you boot up, they basically, if you know what BOGO MIPS is in Linux, like when Linux boots up, it runs a little micro-benchmark that then says, here's how fast my CPU actually is, right? You can see this. Is it proc CPU info? Where is it? I should just search for it. I should have piped it, sorry. We're at the top, right? See the BOGO MIPS? Bogus, million instructions per second. So this is some micro benchmark that Linux runs when it boots up, and now it has an estimate of how fast your CPU is, and it uses that for scheduling decisions, right? But obviously, it's not an accurate estimation of what the speed of a CPU is, but they need something similar to like a weighting factor. It gives them some kind of number like that. So that DB2 is basically doing the same thing, but not just for the CPU, for everything, right? If it's a distributed system, how fast can you send things over the network? How fast can you put things into memory? If you're running a multi-user environment, they're going to try to estimate how many queries you're going to run at the same time, therefore how much time you expect a query is going to block trying to access some resource or some page from another query. So they have a very sophisticated suite of micro benchmarks they're going to run, not just like CPU time, and then they're going to use the results of these micro benchmarks as the input for its cost model. And as far as I know, these aren't actually queries. They're just like internal, little programs that run tests. Small base was an in-memory system out of the 1990s. This actually came out of AT&T. This came out of AT&T. It was called Data Blitz. Then it got renamed to Small Base, and then it got renamed to Times 10. And then Oracle bought them in 2006, 2007. It's an in-memory database. It's still around today, but I think Oracle basically uses it as a cache in front of regular Oracle. But they would have this sort of two separate phases where the developers, when they were building the system, they would figure out, well, here's all the low-level operations that my database system is going to do when it executes a query, like open a table, close a table, scan a page, read a page, and so forth, right? And so they would come up with a bunch of micro benchmarks for all these different operators you could possibly have, if you're familiar with like SQLite has its operands and its VM when it runs a query. Think of like taking all those things, making micro benchmarks for them. Then when a system boots up, it then runs those micro benchmarks. Now it has the CPU and memory costs for every single operator or sub-operator or operand within the database system. Then now when you say, okay, what's the cost of executing this query? They would have formulas that say for all those operands I'm going to have to execute, I know what the waiting cost is going to be, and just sum it up for the query plan, right? And for every operator, you know I'm going to execute these number of operands, and therefore I know the cost of all those operands because I've run those micro benchmarks, and that gives me an estimate there.
Didn't you say earlier that it's too expensive to do this, to run small benchmarks for each operator?
Sorry, statement is, didn't I say that it was too expensive to run small benchmarks for each operator? While you're planning a query, they just do this once when you boot up. Then they get those constant factors, right? Yeah, certainly when you're planning, like if I'm looking at 100,000 different query plans for a single query, I can't run this, right? It's just when I boot up. Again, like BOGO MIPS.
Isn't this like a slightly weaker approach in the sense that if you have a filter below a join, then the cost, if you micro benchmark the join between two tables to be X amount, the filter is going to change how much that operator's cost is.
So his statement is, won't this be problematic if now I'm saying to execute this operator, it doesn't depend on you're basically saying it doesn't depend on the number of inputs coming in. Yes. Yeah.
So how does this work?
So this would be like think of like low level to read one tuple. How much work do I do? Like one probe of the hash table. How much work is that? So then you multiply that with the number of tuples I expect to come up for my cardinality estimates, which is the logical cost, and then I could convert that to be the physical cost. So again, I know Smallbase does this because there's a paper about it, right? DB2 has a blog article from Guy Lohman, the guy from Starburst. He's got a paper. He's got blog articles and the papers talk about what they do. For SQL Server, I don't think there's anything there. Teradata and other enterprise systems, I'm not aware of what they're doing, right? All right, let's finish up quickly. Everything I talked about today is great, assuming you have access to the database, or access to the data, or you know what the data is going to be when a query shows up. But in sort of the modern era with these data lakes or lakehouse systems, you have a bunch of files on S3 or whatever your favorite object store is, a bunch of Parquet files, ORC files, whatever you want, CSVs, worst case scenario. So now a query shows up, wants to access them. It may be the case that your data system has never seen those files before. Like someone put them in S3 yesterday or an hour ago. Now you're being asked to run a query, or essentially to estimate the cardinality or on data that you've never even consumed or scanned, right? Because again, in these lakehouse systems, the database system is no longer in charge of storage. It's no longer managed storage, meaning like in order for me to insert data in, like I just did in my example on Postgres, I got to go to the database system and then insert it so the database can see the data as it's coming in. In these lakehouse systems, it's a bunch of files in S3, and the data system wasn't in charge of putting them there. Some Python app or some other random thing put this data in there, but now I got to run queries on them. So the challenge is going to be, how can I even do cardinality estimations on data that I have no statistics on, right? And so this is called with in-situ data processing, right? The idea is that you're going to execute queries on some object store if you've never seen them before. There's a paper from Dremel from Google and the system called Dremel, which is the internal naming of Google BigQuery, and they talk about how like some large percent of the queries that they execute are going to be on files that they've never seen before because they were generated by some third-party application. So the challenge is going to be like, again, how can I do cardinality estimations here? So the answer is going to be you can't. And in the case of in systems like Snowflake and BigQuery, they're going to instead make sort of worst case guesses on what the estimation is going to be, but then they're going to set the query up in such a way that, or execute the query in such a way that they can adapt and change the behavior of the query, or basically change the query plan on the fly as you're executing queries. Other systems will run and then see whether their estimations are incorrect, and if they are, then they record what they saw for the portion of the query they've executed, and then go back to the optimizer and say, hey, you thought the selectivity was this, but here's what I really saw when I ran. And then now run the optimizer all over again. So we'll have a whole lecture on how to handle this in both scenarios after the spring break. But I just want to point out, like, again, there's no magic wand that's going to be able to solve this problem for us. So in the case of DuckDB, since they're running on an embedded system, and it's meant to run on anywhere and any possible file you want to throw at it, they can't assume that there's going to be any statistics. So there's a master's thesis that talks about a bunch of the assumptions they're going to make about what the data is going to look like, and then that's going to guide them how to do searches. Like, so they're going to assume that if you're doing a join, that's going to be primary key, foreign key. They're assuming independence and uniformity of data. We'll see that next class. That's what assumption everyone makes. If you have a hyperlog log, fantastic. Use that to estimate estimates or do cardinality estimates. Otherwise, the default is going to be 20%. Why did they pick that number? I don't know, right? Seems reasonable. Now, I'm not picking on DuckDB. We'll see other systems that basically have the same kind of crap like this. We're like, is it wrong? Yes. Is there a better choice? You don't know because it's data you've never seen before. So at the end of the day, you have to tell the optimizer something. And so people are going to pick, pick your favorite number, right? Again, we'll cover this more in detail later in the semester, how to basically overcome this through adaptivity or feedback mechanisms. All right, so the main takeaway from this, the statistics that we're going to be generating in our data system, it's going to allow us to summarize what we think the database is going to look like, so that when we start looking at enumerating different query plan options, we have an idea of whether we think one's going to be better than another, right? And so these going back to what he said at the beginning of the class, like, these data structures are the approximation of what the real data is, because we can't go look at the real data because it's just too expensive, right? But then now, if we're trying to then guess the number of tuples that are going to be coming out of an operator, we're now going to be doing approximations and with some certain assumptions about what this predicate's actually going to do. We're going to make approximations on top of those approximations. So, and then now it's even worse. Now, if you're going to make approximations on the output of one operator is being fed into another operator, and you're going to make approximation of what that operator is going to do, now you're basically screwed, because it's just errors on top of errors on top of errors on top of errors, and the results are actually quite terrible. So again, the problem here is that, and there's no easy way to get around this, we're generating approximations on top of other approximations, and that's going to lead to a bunch of problems. And this is again why in certain systems they try to be adaptive, because they know the optimizer is going to be wrong, the cost model is going to be wrong, so therefore they'll correct it later on. Now there was a comment made, I think, in one of the papers from the Germans, where they talk about, they know that the statistics are going to be incorrect. Like, they know they're going to be inaccurate, but it's okay because they still end up finding what they consider to be a good plan. Because if it's a crappy estimate for all queries, for all the operators, or as you enumerate things, then it's okay that they're all equally crappy, but you're still finding the best crappy plan, right? So that in some cases, if you're smart and can quickly enumerate all possible choices, you'll find what actually is the best plan, even though your estimates may be incorrect. I don't know if that's entirely true, but again, we can't prove that because the problem is so complex. All right, so next class, we'll take all the data structures we've done today, and then start doing cardinality estimates on the operators and predicates of those. And so today's class, obviously, there wasn't a reading review required, but for next class, again, we're reading another paper from the Germans, and you should submit a synopsis for that, okay?
Look good, brown. Matter of fact, hold the fuck. This is like that wood grain type of shit. Shout out to Block House, my dogs. Catch one, Big Al, Mike Stroke, Gumby, all that nice. I'm not the one who be amping up the weak ass rhymes. If you spit, if it don't rip through your mind with a sweet anticipated, orchestrated punchline like a reverse the hands of time. Get you captivated quick with the bullshit. I keep the Cadillac equipped for the long trip. I got the remedy for bitches when they start shit. Surround sound like I make them hoes fuck quick and suck dick. Crown me as a thug from the gutter. Shit, some niggas claiming never rapping is sudden. Don't push the button, yes you motherfuckers in front and you don't want nothing. If it did, it'll big star something.